In this video, we will discuss a novel research problem that is quite easy to state, yet appears to have no simple solution. On the screen, you will notice various right triangles with integer side lengths. The solutions, on the right, are given by the Pythagorean theorem, as any high school student will tell you. Like the problem discussed in this video, the Pythagorean theorem is a result that is very easily stated. While proving the Pythagorean theorem is trivial to any undergraduate math student, a simple modification to the theorem, known as Fermat's theorem, remained an unsolved research problem for over 200 years. We hope to convince you that our problem is almost as easy to understand as the Pythagorean theorem, and at least as difficult to solve as Fermat's theorem. For starters, we are given the data of the problem. Namely, we are given a rooted graph G, a traversal sequence T, and a preferred search algorithm. The goal is then to find a labeling of our graph such that the traversal sequence obtained by running the search algorithm is the same as that given. In order to make our problem well-defined and rule out some edge cases, we require that our graph is an undirected, simple graph, which is also connected. Connectedness, of course, means that there is a path from any vertex to any other vertex through edges of the graph. And undirected means that any edge can be traversed in any direction. We define a traversal sequence as an ordered collection of numbers. These numbers will correspond to vertices traversed on the graph using our desired search algorithm as shown on the screen. We now cover the two famous fundamental algorithms for graph traversal and search, breadth-first search and depth-first search. Note that these algorithms are called search algorithms because the process of traversing a graph ensures that you visit every vertex at least once, and this is equivalent to searching the graph for a target vertex. Both algorithms are relatively easy to understand. Breadth-first search will start from a previously determined root vertex. Then you take all of the direct neighbors of this vertex, which is just all of the vertices directly connected by an edge. We call this set of neighbors layer 1. Next, we take any vertex that is a neighbor of any vertex in layer 1 that hasn't yet been visited. You can think of this as going deeper into the graph since every vertex in the layer 2, is one vertex removed from the root vertex, whereas layer 1 was all the root vertices neighbors. Continue this process of putting vertices in layers as you visit them until you reach a point where there are no more neighbors of any vertex that haven't been accounted for. On the other hand, depth-first search drills down into a single vertex at each step, and when there isn't another vertex to drill down into, the algorithm starts backtracking so it can find a new vertex with an available neighbor. We now note that for our problem to be well defined, we must modify our search algorithms, BFS and DFS. In particular, there usually comes a point during these algorithms where a choice must be made. Most implementations make this choice arbitrarily as it doesn't affect the search algorithm's key properties, such as runtime. For our case, however, we will insist that in the case of an ambiguity in which vertex the algorithm will visit next, it should always pick the one with the lowest valued label. With our problem well defined, we are now in a position to look at a couple of examples. We will note that some interesting behavior crops up when we consider something even as simple as the graph shown on the screen. First, notice that with trial and error, we can pretty quickly come up with a labeling where DFS will give rise to our target traversal sequence. As shown on the screen, there is some methodology to how you should choose your labeling. Namely, by keeping track of the lowest possible label we can give to a neighboring vertex, that is, without invalidating our sequence thus far, we can greatly trim down the number of possibilities at each step of the search. This approach is the main contribution of the authors, and in fact we give a fully implemented recursive algorithm. You may now be thinking that with this algorithm, all possible traversal sequences on the given graph have some labeling that give rise to them. What is especially interesting about even this simple example is that with a slightly pathological modification to the traversal sequence on the screen, we can prove that there is no possible labeling where DFS will follow this order on the vertices. This is also a property of our algorithm. Given its recursive nature, we are able to make an informed exit when a sequence will be invalidated later in the search and quickly rule out bad labelings this way. As you can see, with the careful bookkeeping of our recursive algorithm, we can quickly rule out the bad labelings and in fact prove that there is no possible labeling where DFS will follow the desired traversal sequence on these vertices. We conclude by letting our algorithm run in the background on a graph with 21 vertices. Note that this is firmly outside the realm of solvability by trial and error. Please check out our GitHub in the description for an implementation of the algorithm and more information.